Alright, so this here is a pretty tough problem. We have a bunch of different concepts at play here, including that dependent motion, those chord equations. And the question is, how heavy, how much mass should we put in this block so that this one moves upwards at a certain acceleration? So, I'm kind of playing this out in my head. We can figure out the acceleration of this one no problem because they give us some kinematic information. They give us a distance it has to move up and the amount of time that it should take to move up that distance. With our kinematic equations, we can figure out the acceleration of that block. Now the next thing that pops in my head is if I know my chord equation, if I have that all written out, I can, with this velocity or this acceleration, I can figure out the velocity and acceleration of this guy. So from there, we'll have the acceleration of A through that chord equation. But if I do a really quick FBD on that block A, that's still not enough because we have tension, that's going to be one unknown. And we'll have another unknown, the weight. So even though we know the acceleration, or we would know the acceleration of this block at this point, we still have the two unknowns of the mass and that tension. But of course I remember from statics that I can do sort of free body diagrams on these pulleys to relate the tension here to the tension on block A. And that shouldn't be too hard. If I call this tension T, I see that I have a pulley here. All of this is one rope, so all of these ropes here are activated with the tension of T. So looking at that pulley at D, I know that I'm going to have a T here, and a T here. Which means that this downwards tension must equal 3T. So then that clears it up for me. We can figure out the tension here, because we know the acceleration here, so I'm sure we can figure out this tension. And once I know that tension, essentially I'll know the tension, this guy, acting on that block A, and then that will just leave me with one unknown when I come to this equation here, that FBD for block A. So it seems like the plan is there. We just got to do the work and run our math. So we'll start with that block B. It's on an incline of 60. Now we'll have a tension T pulling up. We'll have a normal force acting perpendicular to the ground. Of course, we'll have the mass as well. They tell us that the mass is 5. So if I do 5 kilograms times 9.81, I'll find that my weight is a 49.05. And I'll set my X to be this way, my Y to be this way. Usually a good idea when your motion is tilted or on a ramp, you align your coordinate system to that as well. My tension, only in the positive X. My normal force, only in the positive Y. My weight, though, is really in both directions. So this is that force vector that I'll have to split up using a right triangle to grab its components. Here's my negative Y-axis. So I'll want to find this angle here. And we can do that by just creating an imaginary horizontal line right here. This guy's going to be 60. Because remember, 60 is just the angle in between the ground, or horizontal line, and that slope line. Same thing here. Here's our slope line continued. Here's this imaginary horizontal line I created. Therefore, this is our 60. So if this is 60 and this is 90, that means that in between here is going to be a 30. And this will be a 90 right here between a horizontal and a vertical, which means our angle that we're looking for is right here and is 60. So I know I can do the cosine to get the negative y component and the sine to get the negative x component. And of course it's the hypotenuse here that is the 49.05. This is the vector itself. These two are just components, smaller parts of that vector. So I can do my sum forces in the x and the y here pretty easily. So here's my sum forces in the x, all of tension positive, and I grab that negative x component of the weight using the sign. Of course, the normal force is not in there, it's only in the y direction. And I can figure out this acceleration using that kinematic information that they gave us. Remember from physics, we were taught those 4 kinematic equations. And you can use these equations as long as you know the acceleration is constant. And long story short, we know the acceleration will be constant here because all of our forces are constant. I mean, the weight will be constant, this weight will be constant, and because of these weights, the thing is going to move, it's going to create these tensions, and all of these forces will be constant because we have our driving forces, the weights that is, the things that create the motion, these driving forces are constant. And of course, if the force is a constant, if this is a constant, and this of course is a constant, the acceleration is a constant. So it's always good just to walk through those technical details and just make sure you're clear to use these constant acceleration kinematic equations. This is the one that I find myself using the most. At times equal to 0, we'll just say that our x position is 0. We start from rest, so our initial velocity is 0. And we know that at time is equal to 2 seconds, our x position is 0.75. So we can crunch all this math and figure out our acceleration. And we'll get a positive 0.375. So we'll use this right in here and we can figure out that tension. And I could do the sum forces in the y if I wanted to. That would allow me to figure out my normal force, but nothing in the problem has caused me to think that we need the normal force. So if I put that number in here and run my math, we'll figure out that our tension is a 44.35. So now if I set up my free body diagram for A, we know that we have a tension going up. And we've already discussed that this tension here is 3 times that tension attached to B. And a couple of people have asked me, wait, how can we say that these tensions are equal to this one if our pulley is moving? We were a lot more comfortable doing this in statics when things weren't moving, but everything's moving in this case. Well, if you do a free body diagram on that pulley there, yeah, we have 3 T's going up, we have an unknown going down, and of course sum of the forces is equal to mass times acceleration, so definitely have a point here. It's just they're saying that we should neglect the mass of the pulleys and the chords. So my mass is 0, this whole side here is a 0, and the sum of my forces must add up to equal 0. So again, we can say that if I have 3t going up, I must have this equal to 3t going down. So here I basically know that I have 133 newtons going up, which is 3 times our tension there. but I don't know our mass, so I don't know the weight. And because I also don't know the acceleration, I don't have enough information to figure out that mass. But we can figure out this acceleration by doing our chord equation approach. So don't forget that chord equation approach. I want to create position variables that allow us, oops, should be B, that measure out the positions of each one of the moving parts of our apparatus. And I see that this block and this pulley right here are really rigidly tied together by this like metal link right here. So since they move together, I know that from our work on learning chord equations that the velocity and the acceleration of these guys will be the same, and therefore I don't really need an extra variable to track out A specifically. I can just make a variable that tracks out pulley D. I'll call that, you know what, I'll just call it SA, because block A is our thing of interest here. So our rope will have some length. So I'll start grabbing this portion of it, and that'll be SB. Going further, we have this little constant right here. No matter where the blocks are moving, there will always be a length of rope there that doesn't change. So I won't write that one. Continuing, I have this right here, and that's our SA variable. So plus SA. Some more rope that will just always be there and whose length will not change. And then I have these two things right here. I got to be careful because these are not SAs here. Yes, they do sort of reach out and they terminate on this pulley D here. But I got to be careful how I capture these lengths. These lengths will be getting longer as our block A drops. But I noticed that this is a constant right here. Some constant, I'll just say C1. And I see that I can form these two blue variables here by doing this length minus this length. If I subtract that green line or that yellow line from that green line, I'll pick up this blue length here. And I want two of them. So I'm going to do SA minus that constant C1, and I'll multiply it by 2. And I know I said, and I ignored the constants in the beginning. Here I'm just being extra careful. Remember, you can always include the constants, and when you take the derivatives, they'll just become 0. But I'm sure this guy doesn't have any effect. I bet I could have just written 2SA, but I wanted to be extra careful, so I just included him. If you're ever unsure, feel free to include any of those rope constants to form your entire rope length. So if I take one derivative, I get a 0. I'll call this SB dot, really the velocity of B. SA dot, really the velocity of A. Let me just distribute those in real quick, that 2 in. Taking the time derivative of this one, I'll get 2 times SA dot. And taking the derivative of this whole thing is just going to be one big constant. It doesn't change with time, so really the derivative of it is going to be a 0. And since I have 2 of these SA dot quantities, I'll combine them to make a 3 SA dot. And we have that. And if I take one more derivative, I'll get the acceleration of block B as measured from this origin right here, that datum. And that's going to be an important distinction coming up. And SA double dot. So we have to be extremely careful here. These are the velocities of A and B and the accelerations of A and B. Let's focus on SB real quick. The velocity of SB, or block B. This is the velocity of this block, but measured from this sort of origin right here, this datum. And therefore, the same thing for the acceleration. The acceleration of this block measured from this datum. Got to be careful. This right here is the acceleration of B measured from here. Remember, when we worked on this stuff over here, our coordinate system was such that here was B, my x was positive up this way. In this case, in the case of my work here, it's reversed. My origin is right here, counting positive down the ramp. And this could cause big problems. Look over here. Let's say that our block moved up. Well, that would be a positive Vx, a positive velocity. Now look at our picture over here. Again, if that block moves up, our SB variable is going to be getting less, which means SB dot, the velocity of B as measured from this origin, SB dot is going to be negative. Pretty crazy. If this thing goes up, my velocity for our coordinate system based on variable x will be positive, but my velocity here based on coordinate SB will be negative. Now the same argument goes for acceleration. So what I always go through this argument. So what we're going to say is we're going to say the acceleration of B, but using that first coordinate system that we did in our free body diagram, the acceleration of B based on x will be the opposite of the acceleration of B measured using variable s. And notice the same phenomenon takes place for here. When I did my sum forces in the y, this whole thing is based on variable y. And variable y is defined as positive going up, and I should have put that there. I kind of reflected it there. But what I should have written was that, yeah, our y coordinate is positive going upwards and negative going downwards. So imagine this. If block A was to move down, which is what is happening here. So block A is moving down. Well, as we can see here, this is going to be negative velocity based on that y coordinate. But looking at our chord stuff here, if this thing goes down, that SA variable will be lengthening. So therefore, SA dot, the velocity of A, but measured using the variable SA rather than this y, that SA dot will be positive, whereas the velocity with respect to y would be negative. So again, we'll have to do a similar negation for SA double dot and AY. So I'll write that out. So the acceleration of A in the y will equal the opposite of the acceleration of A as measured through our chord equation variable SA. And I'll just change this right here. Acceleration of A in the y, acceleration of A in the y. So this negation argument is very important. Just make sure you ask me questions in the videos if something doesn't make sense. So I'm going to box up these two negation equations here. And our acceleration of B is a positive 3.75, Well, plugging in that positive 3.75 here, we'll know we'll get a negative 3.75 for SB double dot. So I'm going to write SB double dot is equal to a negative 0.375. Now with this, we can run that through our actual chord equation. Plugging that in for SB, we'll divide by 3 and get SA double dot. So SA double dot will equal a positive 0.125. And you'll always want to be making sure this makes sense, these numbers. Our blue, or our purple, or B, is moving upwards. We know that for sure. So we know that this SB variable is getting less and less, which means the acceleration should be negative. That makes sense. And of course, since these motions are tied together with this rope, we know that if this guy goes up, this guy's going to go down. This variable here is going to lengthen. It's going to get bigger. So therefore, it makes sense that this acceleration is positive. But of course, I've got to reroute this number through my relationship between these two coordinate systems, these two variables, S and Y. And I'll have to negate this. So I know that the acceleration of A in the Y is a negative 0.125. And again, that makes sense because look at our work here. Y is positive up, but we're moving downwards, we're accelerating downwards. Of course, the acceleration with respect to Y should be negative. So you should always be able to run the math and just make sure it makes sense. So with this, we can work our equations here and basically figure out our mass. If I plug in a negative 0.125 here, and of course gravity is a 9.81, I can figure out the mass of A necessary to make all this possible. And of course we'll get a positive number, and that number is 13.73 kilograms. Alright, so quite a few things going on. FBDs, splitting up vectors using triangles, kinematic equations, chord equations. Got this negation thing you really got to watch out for. So please post any comments you may have, and I'll do my best to respond to them promptly.